Welcome everybody. This is a update from last year on Rust-on-Zephyr with an obligatory DALL-E slide with a nice logo for Rust and Zephyr, or the other one it generated the first time. I don't know what that's supposed to mean. So last year I gave a talk, it was either last year or the year before, I'm fuzzy on that, about Rust-on-Zephyr. And at that talk I presented the wonderful program of Hello World. I got a small Rust application with main that ran as a Zephyr application, and it printed a message over the console. It's very manual, lots of issues with linking and the conflicts with LLVM and GCC and all that kind of stuff. So what's happened in the last year? So just kind of as an overview, I will show some pictures. Just after that conference then, I got infected with the build your own keyboard virus. And so I've been making a couple of these things. This was called Proto 2, or Proto 3 for lack of a better name, and Proto 4 is my current iteration. You'll notice a theme with the number of keys. These are either 30 or 42 key split keyboards. Various layouts. They have onboard steno translation with the dictionary. It's like a little over 4 megabytes with all kinds of fun, exciting algorithms that I would never want to try to implement in C. The code does scanning, debouncing, chord modes, USB, all this stuff. And I started with Qmk, like a lot of people do. It didn't take very long to get firmware running with Qmk, but I wanted to do it in Rust. So I started writing my own code. With Rust embedded, working with some of the people behind that. And it works. Started running into a lot of issues with the HAL support, and Rust embedded is kind of mixed bag as far as how good it is. I'm like, you know, I also work on Zephyr. I did Rust on Zephyr. This might be a good combination. So I moved the keyboard firmware to be written in Rust, running on top of Zephyr. And we'll get to in a minute why it's not something I don't mind sharing it, but it's not something that's usable to anyone yet. But so my firmware right now is about 5,900 lines of general Rust that didn't change when I moved it from Rust embedded to sit on top of Zephyr. By not changed, there was less than like 10 lines of code that had to change for various things. There was I don't know why that's such an exact number, but like 1,600 and some lines of code with comment, it's not slot count, of Rust embedded specific code. Most of that living in a file called main.rs, and it's really fragile, was the thing I discovered about Rust embedded. It doesn't really handle the idea that I want to work on multiple targets. And we get spoiled in the Zephyr world that you can say West build and pick a different board and your code just works on a different board. With the way Rust embedded, your main has all these things in it, and like the GPIO pins each have their own type, and so when you want to declare a variable that holds one, well, that changes when you change different targets because they're on different GPIOs, and we'll see where that goes because somebody's going to have to figure out that, oh, we want this to actually be useful, so rather than strongly typed. So I don't know where that's going to end up, but so I ended up writing about 2,600 lines of code to make this thing work on top of Zephyr, along with like 500 and some lines of C code to glue it together. But the important thing is that there's only 1,300 lines of code that are for the keyboard, and those were mostly copied from the Rust embedded code. That was some of the matrix scanning code and stuff, because it's directly interfacing with drivers is a bit different. The rest of that code is the Rust-on-Zephyr support code, which is still embedded in my keyboard firmware, but what I'm going to talk about today is how do we go forward with this so that Rust-on-Zephyr is a thing people say, oh, I want to do that, and they can go do West build, set a board, and then just point to samples Rust such and build it, and that it not be 1,500 lines of code in that thing. So I made an RFC, I don't know, 3 or 4 months ago. You can go look at this. The goal of this RFC is application development on Rust. People are always like, when can I write drivers in Rust? And The simple answer is this is step 1, that's step 3. So we'll get there, but that's not the focus here. This should be in the Zephyr tree. The goal is that you should be able to do Rust up, get a stable Rust compiler, have your Zephyr tree that you just built, that you just got, and build a Rust application on top of Zephyr. It should feel like you're writing Rust code. I know there's people that are writing Rust on Zephyr now, like me, and you end up with a lot of these little wrappers and lots of unsafe sprinkled all over your code, and that's not what we want here. This should feel like writing Rust code. It should feel, when you want to do a channel, when you want to do a mutex, it should feel like you were using the one in standard, just it happens to work on top of Zephyr. So, how do we get there? What's involved? And what I will say is that my tree is a hack, that my firmware, to figure out what are all the steps and pieces we need to get there, and then work will be making this clean and putting it in the upstream tree. So, how do we build this? If you're familiar with Rust, Rust has this thing called cargo, and it runs the world. You have a program, you build it, you type cargo build, and you get an executable. You type cargo run, it runs it, you type cargo test. It's really nice. Zephyr has the same idea. You type west build, you type west flash, you type west different things, and you get your build. How do we mush these things together? So the cargo system has one little thing that you can do, and you can tell it to build a library, and it will do all its magic, and then it will generate a .a file buried in some directory, but that's fine. So we're going to let cargo do that. But it needs to know a bunch of things that came from Cmake as far as Zephyr builds. When you do a build, what is the target? What Kconfigs are set? There's all kinds of stuff going on there. So there's a bunch of pieces here. So what happens, and what have I got working here? So there's a Cmake mapping between Zephyr's idea of build targets, which is done through a combination of, it's Kconfig entries set by a board and possibly an SOC and some other things that decide what target you're actually on. In Rust, it's an LLVM target name. It's a triple of, or 4, of strings separated by hyphens that tells it exactly the configuration CPU that you're building for. We also have some crates that are going to be Zephyr specific. There's a Zephyr sys, there's going to be a Zephyr, there's going to be some things with device tree and Kconfig that we want to own as the Zephyr. We want those to be part of the Zephyr. They're going to be modules. And so we need to add these path overrides so it doesn't go try to grab these from cargo. There's also some issues with, if we have dependencies, the project policies of Zephyr are going to require that we vendor those. And so we want to be pointing to the vendored versions of those. And a couple other things is, if you just go into my directory right now and haven't set this up and you type cargo build, it will spew all kinds of garbage out because it's trying to build for your host and doesn't have Zephyr packages and all this stuff is missing. So one of the goals was to generate a template for the .cargo/config.toml so that you can just type cargo build. It won't make an executable, it will just do the part that cargo is doing. But importantly, your IDE will just magically work at that point. And you can, do function completion. You can go look at other code in different crates and everything. Some other things is the Cmake lists file in your Rust application. It should be small. If you look at some of the sample ones right now, they're usually 4 or 5 lines of actual Cmake stuff, and several of those are just required by Cmake. And we want something similar that's like, oh, I have a Rust application. Here we are. So what are the details? This is where I've learned more about Cmake than I thought I would need to know and kind of want to know, but I had to learn this. So there's some things in here about, this is an example just for the Cortex-M of you picked a target on Zephyr. What do you pass to Rust as far as the Rust target? As you can see, there's a lot missing here. This won't just run on ARM, but we want it to run on the Cortex-M. Oh, and then there's a fun comment in there about the ARM v7 ARM v8 FP tag in there. So I mentioned that .cargo config. Here's the Cmake, part of the Cmake fragment that builds that. This just writes a file. It's in the build directory, so you'd have build, and then this would be build / I forget the exact name I called it, and you can actually just symlink that to be your cargo config, and then things work for you. There's a custom command that, based on, this was the not fun part of Cmake to figure out. Cmake was very, very upset with the idea that I had a command that I need to run, and I need to always run that command, and it has a whole bunch of things that it knows that we don't need to tell Cmake about. And so it turns out the way you do this is you make it depend on this dummy file that never exists, so it always tries rerunning it. And then you say, oh, and as a byproduct, we produce the .a file. So this runs cargo. And all these lines that you see here are the same things that are in the .cargo config. So in a sense, they're redundant, but this means that Cmake can build it before you actually symlink that file, because otherwise there's this kind of catch-22 problem. So with all of that, and this won't live in your tree, this is going to be off in a Cmake function that you would just call from your Cmake file. But this allows this whole process of, so what happens when you do West build? Cmake does a whole bunch of stuff. It figures out, it runs Kconfig, it generates a bunch of files, all this stuff. Then it gets to where it needs to do things. It compiles some of the Zephyr code, then it runs cargo, and it compiles some of the other Zephyr code. The ordering there is not, I mean, I'm sure it's deterministic, but it's not determined, if that makes sense. And what you end up with is it runs cargo in the middle of your West build, and then you get an application, and you can run it. So, Kconfig. This is very different than what Rust thinks. Rust likes the idea of you have features, and they live in your cargo.toml file at the top of your source tree or project, or some different options there. And Zephyr has its own idea. It has this thing called Kconfig. There's all these configurations, there's dependencies. It's vastly more complicated in use than is typically done with features in Rust. So the thing about Rust is there's kind of some definitive things. In C, we can have pound defines that we if-def on, and you can have source files that change what's defined. So we have header files that might define more things, that might conditionalize. Rust has a kind of policy in the project that the compilation of the conditional compilation cannot depend on anything set by the source code in the project. So these configuration options, if we want them to be visible to Rust code, they have to come in as we run cargo. So what do we do? The idea, well, let's just look at what's going on here. So there's a program that runs as part of a Rust build. And this won't actually be visible to you using it unless you need this conditional compilation. Otherwise, it just happens in Zephyr sys, and it knows how to conditionalize. But the idea is that this reads the generated build/zephyr/.config, or if you're using sysbuild, whatever that it ends up, and it looks through the config options. And there's two things it's looking for. It's looking for Boolean ones, and those become what are called, I don't know how you pronounce it, CFG things in Rust. And so in my Rust program, I can say #CFG config foobar and have a piece of code that's conditionally compiled in Rust based on a Kconfig setting that came from Zephyr. The other ones are things that are Kconfig settings that are strings or numbers and those kind of things. And those get turned into consts in Rust. So these don't generate code, but you can refer to them as either numbers or they're kind of static strings. So that's Kconfig. And when implementing this, just as a caveat, much of this is speculative. So when we get to actually implementing it, things may change, or we get feedback when we post patches and that kind of thing. So that's Kconfig. It's actually the easy one. And we have the device tree. And if you've done Zephyr, you know the device tree is a pretty integral part of how it works as far as configuration, boards, everything about a given build. Much of that is defined by the device tree. So, yeah, did you? Sure, there's not a microphone, but I can repeat your question.
Are we going to get the same wonderful error message about device tree?
I'm hoping to have worse error messages with no. So I'll get into why that. The question is, if you've ever tried to use the device tree from C in Zephyr, and if you get something slightly wrong, you get a 5,000 line error message, not quite, but you get a whole bunch of errors about macros. So the way this works is there's code that runs, that reads the device tree. So it generates it's not a flattened device tree, I don't know what we call it. It's a device tree that's canonicalized. It doesn't have any conditionals in it. It's been through the C preprocessor. And then we walk through that based on a bunch of YAML files that describe what is allowed in the build. And then we generate this file by stitching names together of the tree. So the device tree is a tree. That shouldn't be surprising. And we stitch the node names together with conventions, kind of similar to how you might make variable names in a language like Rust or C++, where you have modules, but the linker needs to see them, and we don't do it with Z's and numbers, but we do it with just, I think they're just like underscores, and we have an N for the root and that kind of thing. Needless to say, that's not a really good solution for Rust. If anything, the ability to stitch names together in a macro is an unstable feature. And one of my goals is to try to avoid needing to depend on unstable. But in Rust, we have modules. It's a hierarchy of names. It maps really, really well to the device tree, which is a hierarchy of names. So let's just make that. We have a device tree. We have a module tree. Why not make them one-to-one? So what do the things in the device tree end up with? Because I talked about, we don't want to generate code or stuff that takes up space in the target from the device tree. We want it to be things that are available at compile time. And then obviously if there's things in there that are needed as structures that need to be in the code, they will be, but it's not going to be this big data structure that represents the device tree. So there's a lot of things that are just consts. The device tree has a lot of numbers, but there's a lot of other things in there that are kind of weird, honestly. There's the properties are actually, in the device tree, they're just byte arrays, but we don't use them that way in Zephyr. We interpret them before it's compiled down to this flattened device tree. So we actually have like groupings of properties. We have like if you have a GPIO definition, you'll have a p handle and a couple of numbers, and then a p handle and a couple of numbers. And we don't want to have a data structure with that in there that's going to expand in anything. So what I've been doing to start with is using const functions that can return that information. And it works kind of like a macro in C, where it doesn't actually generate code. It's expanded at compile time as needed, but it's still accessible and it's still usable. And if somebody does need it, it could generate code. Like if you needed a function pointer to one of these things, then it would be available. The other thing is the device tree has these things called aliases. You can have, like there's a chosen node, which is just a bunch of names that point to other nodes. And the way we do this or the way that I've started doing this, is you have a module, and then you have this construct in Rust where you can say pub use this other module, : asterisk, and it says, bring all the symbols from that module into this module, and then export them publicly. And so it's kind of exactly what aliasing means, that you now have visibility. So in your code, you'll be able to just refer to device tree chosen UART or console or whatever you, well, we had to figure out the name mangling because you can't have symbols with commas in them, but there'll be a convention. It'll probably be like Zephyr underscore console. So what does this look like? Well, this is I'm forgetting the name of it. It's a parser generator. It's a PEG parser generator inside it's a Rust crate. And then this is a snippet of code, of a description of the device tree source file that this thing then parses, and it generates something kind of like this, with the caveat that I've only done a few of these, that a lot of them just turn into strings that are just then what was in the device tree. So you have things like, the hash address cells from the device tree turns into this N address cells. The compatible is a const function that returns a 2-element array of strings. And the way this works is if you call that function and then dereference it with like a 0, all of that goes away and you just have a string that ends up in the code. And then more and more. So there's a lot more to that. The thing I mentioned with the labels, for example, every node can have a label that refers to something deep in the tree. And so there will be a module that is the labels, that's each one of those is a module that has all of the names in it, so that you can just refer to something in your code by label. This is very similar to the device tree accessors in C, except they're just modules. The nice thing is all of this is visible to your IDE. So when you're in there writing code and you go Zephyr, figure out the names, I type Zephyr : device tree, I can start completing on the things that are in the device tree for my current build, and they're just there. All right, let's take a 5-second break because there was a lot with device tree. Okay, syscalls. I'm also kind of way ahead, so we'll have time for some questions here. So, oh goodness, a number of years ago, we added user space support to Zephyr, where we separate between threads that can be marked as user space threads and then the kernel mode. And in order to get into that mode, you have to make syscalls. And this was done not by drastically changing everything, but by basically going through the headers and marking a bunch of these functions as syscalls. They then don't actually generate, so their headers, the real function gets a different name. Magic happens with Kconfig options as to whether you even have user space. Different code makes a dynamic decision as to whether you're a thread that is in user space or kernel space, either calls the function directly or does a trap to a system call. The short form is there's a bunch of code that reads the header files, looks for these syscalls, generates this table of the actual implementations. Importantly, there's no C function for me to call from Rust, so I can't just say extern C this function. It doesn't exist. And so for my keyboard firmware, I have wrappers for all the syscalls I need, and I think I have a picture of that. Yeah, that's this. You have, sys mutex lock takes these arguments and it calls k mutex lock. And then depending on how you're configured, that may just be the function, or it may expand inline to this kind of syscall check, which checks if we're syscall and then either calls the function or does the other things. So we're generating this kind of C-ish code by reading headers. And I think I want to do the same thing in Rust. Now, I haven't done any of this yet, so this is completely speculative. But we want to generate a Rust module that has all of the syscalls that are in your particular configuration with the syscall numbers that you ended up with, because as we discussed in a different meeting, those change depending on your build. And you have this module that now you can make syscalls from Rust, and they should have exactly the same overhead as they would in C. The syscalls will be expanded inline. They will do the check depending on your configuration. They may just directly call the implementation. or they may check if you're user mode and do the trap as necessary. Now, the interesting thing is they're all unsafe as far as Rust is concerned. You're calling C. We don't have any guarantees. There's pointers all over the place. None of this fits Rust's model of safe pointers and that kind of thing. So this goes into something that's traditionally called like Zephyr sys, where it's an implementation that then there's wrappers on top of. So we want to build above that abstractions. So in the Rust standard library and a bunch of support crates, there's something called parking lot, which is a cleaner implementation of communication channels. There's mutexes, mutices. I don't know quite what the right word for that is. But I want to build abstractions that look like the ones in standard. Just as a caveat, I say, why don't we just implement standard? Somebody's actually done that. There's an implementation. To use that, you grab all of LLVM, the source code to the Rust compiler for an exact version that they support. You mush all of this together, you build it, and hopefully you get a tool chain that has standard that might work with some specific version. Aside from the fact that I don't think it's actually the right solution because we're not a POSIX system. We have some POSIX-like stuff, but there's a lot of stuff we don't have. And I think it makes more sense to provide the abstractions that make sense on Zephyr, just in a module called Zephyr instead of standard. It also has the advantage that you just use regular tools to build this. You don't have to go build a tool chain, because I think that would block adoption of this, that if people have to build a Rust tool chain as well. So what do we do for abstractions? So most of the Rust abstractions assume that the underlying operating system primitives can be dynamically allocated. P-thread create, that kind of thing. So a lot of them in Zephyr can be allocated, but you don't want to do that, at least unless part of this project is about making dynamic K objects more efficient, because the statically allocated K objects go through a perfect hash function for lookups for validity. Dynamically allocated K objects are in a linked list that it scans every single time you use one. So they're useful if you have a few system-wide. They're not useful if you have a large number of them. So some of the solutions are to have like pools of these that are allocated to fix the allocator. That I don't have the correct answer for that yet. The other thing is there's a couple of K objects, like the most useful ones, including sys, mutex, and futex, that cannot be allocated dynamically at all. So that isn't even an option. And I mean, it's literally if, when in the K object allocate, there's an if statement, and if it's one of these two, return an error. It's because there's a user space and a kernel allocation together, and there's not been any code written to manage that. So there's a lot of choices behind this. We can have clean Rust APIs on these wrappers and end up with these things that aren't compatible with C code, or we can have less safe APIs, but then compatible with C code. And I honestly think the answer is that we're going to probably need both. That there will be times where if you're using a library in C that needs a mutex, that needs a FIFO, or some kernel data structure, you're going to have to use that kernel data structure from Rust, and there's probably going to be some unsafe involved. But if you're writing an application that's just in Rust, and you don't need to interface with C code for some of these things, it'd be nice to have these data structures that work like they would in other Rust code. There's no unsafe, I just allocate them, I lock, I do that kind of thing. So I'm guessing we'll need both. Little snippets of the implementation here. We have, and by the way, by implementation, I mean my hacked together thing so that I could do mutex, not one that everybody would want to use. But this is kind of the messy code you don't want to see. But the end result of this is we have this thing called a mutex that wraps around a piece of data. This is kind of the Rust thing that differs, whereas in most C things, you have a mutex, it's a thing, it lives by itself. And then hopefully you keep track of what data goes with it. In Rust, the mutex wraps around the object that it's protecting, and you can't get to that thing unless you lock the mutex. So that's where it gets the additional safety from. It's also why that thing that it's wrapping has to obey Rust's notion of ownership, can be moved with its rules and that kind of thing. But that's all doable. We can do that with the, I mean, this works. When I press keys on my keyboard, there's a mutex around a queue that's keeping that data, and it all works. So, getting near the end here of this, drivers. Now, drivers and device tree are kind of intimately tied together, so the data about given drivers is going to have to come from the device tree, and there'll need to be abstractions, whether these are like macros or functions that are generated, that kind of thing, I'm not really sure. But then you get this device back, and in Zephyr we have a struct device. And all devices are generally a struct device. There's a few like GPIOs that are a wrapper with a struct device in it and then 2 integers to tell you which pin and that kind of thing. But most part, it's a struct device. If you go get your UART, you get a struct device back and you call an I2C method on it, you probably will seg fault or something really awful. It's not strongly typed or anything. And in Rust, we'd like these things to be typed so that the methods on the device are methods on the particular struct. So this is going to be a good amount of work. I mean, my goal with this is to start with some subsystems, but realistically, I think this is where hopefully the community starts to get involved and somebody says, I want this device. And there's a lot of things that have to be figured out. The devices are kind of different. There's still a lot of stuff that's built around callbacks, which is hard to do safely in Rust. It can be wrapped, but there's also this kind of move to make, those don't usually work from user space either, is the issue. So it's kind of ad hoc, and there's a lot of case by case is what it comes down to. What I did is basically, I have the sys wrappers for the device, the actual calls that are there, because they're system calls, and then I'm wrapping the device, the struct device, in a GPIO struct, in this case, that has methods on it. So in the Rust code, I can say, set, clear, toggle, the different things that map to these functions here, configure, and I just use them and there's no unsafe involved because the type system made sure that that's the right thing where that makes sense to call. But this is a big part of the work to do this. So the last thing I want to talk about here is logging. And Zephyr has a fairly rich logging system. Well, actually, Zephyr has several fairly rich logging systems, and you pick an implementation that you'd like. What I'm doing right now, just to make it work, is when you do a log message in Rust, it mallocks the end resulting string. It just uses format, and then that's passed in through a C wrapper to log that into Zephyr, and then it gets freed. This kind of automatically happens, but it's not very efficient. And so we have to think about, Zephyr's doing log messages with formatting, but it's printf. It's %d. It's its own specific style of printf formatting. So what do we do? Rust has its own thing. They use braces. It looks more like the Python one. There's different indicators. Most embedded things in Rust have restricted subsets of them, so that's certainly an option. But one option is, should Zephyr's logging mechanism support pluggable formatting for the delayed formatting so that the Rust logging could do it in a similar manner where here's a format string, and some arguments, and then that gets generated when the log messages go through. Another option is there's a package for Rust called Definite. I don't know how you pronounce that word. It is a host deferred formatting. So when you say log, or warn, and then you have a string and you have some arguments, the string never makes it into the executable at all. And what gets logged is an index and your arguments. And then there's a host side program that pulls that down, expands the string. It works really well until you forgot to stop it and restart the little host daemon and you're out of sync and your strings are nonsense and you get really, really weird messages. Again, I don't know the right answer to this, but there's a lot of possibilities. I mean, ideally, we want it to be low overhead and work with the existing Zephyr logging. What I do now is I have macros that work like the log crate in Rust. So you have a macro called error that takes formatting arguments and it logs it. And what I do is I call alloc format. I put this into a string and then I pass this off to this C wrapper that I wrote called log message, which just spews the message, queues up the message in the Zephyr logging system. So this is like, if you picture how I've moved in my code from clean to complete hack, this is the most hack aspect of it all. So that's it for what I wanted to share with topic. And we've got, I think, about 3 minutes left for questions and that kind of thing. So, and I see like 37 hands, so Brix, you've got some work to do.
So I have one question out of curiosity. Why enable user space? What is it necessary?
No, but
Okay.
it feels wrong to not let it work. I mean, I guess it's part of it.
Okay.
So the question about why user space, because I think there is still reason for it if your application. So one reason to not need user space is, well, we're writing Rust code, it's safe. But maybe that's not the only code that's on my system. Maybe there is also other user space things, and I still want that separation. So I think it should work still.
So are you using the Rust standard library? And you mentioned using crates, so that's
No standard.
No standard. Okay, thank you. So you're doing classic embedded Rust, basically.
With alloc.
Okay, and then what are the size implications, like in terms of the .a that's now being built in? Were you seeing any size constraint issues? Because we tend to care about that a lot in Zephyr, or not?
Yes and no. I mean, I'm thinking a little bit about it. The problem is my builds right now, I'm pulling in like format, and that tends to overwhelm all the rest of the system with, I had one thing where I'm on a no hardware float point target, and I did a little bit of floating point math to print out a nice number for a log message, and it added like 35K to my application. So I haven't actually started looking at that yet. Yeah, there's definitely some concerns with, does Rust make everything big? But if you're careful, it doesn't have to make it that bad.
I was just wondering, do you use anything like bindgen, or are all these wrappers manually written?
So I'm not using bindgen currently. And that's kind of a big question. Like the syscall thing is going to be bindgen-like, and I don't know if that will be our own version of bindgen that knows how to do that, or if it's flexible enough to do that. But yeah, there's all kinds of structs that are full of if-defs and stuff, and that we do need to map, and it'd be nice to not have to maintain that by hand. So, but I don't know if that answers the question. Basically, I haven't looked at it yet, but it might be useful.
Could you use a combination of pinning and RepRC to hold those mutexes in Rust and still pass them to C safely?
So currently, no. I mean, yes, I use RepRC, but right now, all of the things that Zephyr needs to know about that need to be at specific addresses have to be statically allocated. And so currently, my implementations, you have to pass in a const star thing to it as part of this unsafe init, and it's a problem we'll have to figure out how to solve, whether there's pools, whether we do get some kind of dynamic allocation, but they're special and magical from Zephyr's point of view. They happen to be pointers, but they're better thought of as abstractions, as just bits from Rust's side. They're not, we don't get to allocate them. They're not in memory that's visible to us. We're just, their handle happens to be their address on this, in Zephyr memory, so.
Great talk, David. Couple questions for you. So,
Sure.
I guess, have you looked at, so Zephyr has many struct objects, right? It's just a bunch of function pointers. Have you looked at how Linux deals with that, with, proc macros to sort of, match those things up well?
Not yet.
Okay.
The way I would say this is I'm doing these by hand right now to understand what needs to be done. Then when we get to, well, now we have, thousands of these, what do we do to do that? And I'm sure that there's a lot of work like the kernel has done, the Linux kernel has done, that could be helpful with that. As long as they tend to venture rather freely into unstable. And I kind of would rather avoid that just for usability.
And I guess, my next question is more broader. I mean, having done all this, to sort of try things out and sort of, do you have some notion, is it worth it, right? Is it worth
Very
the
much
complexity to do all this? Yeah.
Very much so. At this point, working on my keyboard firmware is quite pleasurable. It feels like I'm doing Rust development. It feels like I'm doing Zephyr development. It's like the best of both worlds seem to come together. The edges are really messy still, and when I have to do something new, I end up spending a day writing a whole bunch of code to go do that. But when I'm off working, I do my development in Zephyr, and I'm getting the stop notification. When I do my development in the keyboard firmware, I have this crate over here, and it runs on the host. It has unit tests. I do cargo test in that directory. I make everything work. And then it gets pulled in with no standard into my application, and it just works because it's been tested and all that stuff. So, there's definitely a lot of that. I think that's all the time we can keep talking out there if we need to. Thank you.